Hello, my name is Martin Kennedy with matrix number 84433, and today I'm going to go through question 1 for the assignment. So for this assignment, we are going to find the value of the current for the voltage of 5 volts. So based on the table given, there is no 5 volts in this column, but we do know there is 5 volt in between 4 and 6. So from here, we can put the voltage of 4 as V1 and the voltage of 6 as V2. Same goes for the current. This one will be I1 and this will be I2. So from these values, we can find the current. So for the first method, which is the Lagrangian method, we are going to find for the first order. So for the first order, this is the formula. And from this formula, we can get the value. And from this value, we can sub into the formula and get the answer of 4 milliamps. So for the second order, this is the formula. Same thing, except there is one extra value, which is V0. So for this V0 will be the value before V1. So this will be V0. And will be the corresponding I0. So from these values, we can sub it into this formula. And we can get the answer of 4.0125 milliamps. Same goes for the Newton's divided difference method. We're using the same value, but with a different formula. And then if we sub in the value with that formula, we can get 4.05 milliamps. Same goes for the second order for the Newton's method. We can get the answer of 4.04 milliamps. So if we were to compare all of these values, 4 milliamps and 4.0125 milliamps for the Lagrangian method, we can say that the second order is more accurate. And for the Lagrangian method, this one has the value of 4.05 and this one has the value of 4.04. So here we can average it out and say that the answer would be around 4 milliamps with the error of plus minus 0.03 milliamps. So that is all from me.
Hello and hi, my name is Henderson Tutuan Anthony with matrix number 84004. Today I will be presenting a solution for question 2. Question 2 is compute the energy stored in the capacitor using E equal to integration 0 to 10 PV dV, where P equal to V times I by using two numerical methods. Compare result from the different methods and conclude your findings. So from this data, we know that this is V0, V1, V2, V3, V4 and V5. So our N is equal to 5. And from this, we know this is B and this is A. So our B is 10 and our A is 0. So from this data, now we can find H. H equal to B minus A over N. So H is 2. So the first method that I use is trapezoidal rules, where the formula is this. And then for this solution, we got this equation. And then this one is we need to find the function for the P. So we know that P times AP equal to V times I. So we just multiply this and we got this. Substitute into this equation and we got E equal to 271 millijoules. So for the second method, this is the formula, and for the solution, we got this equation. Substitute the value and we got E equal to 223.06 millijoule. So the comparison for this solution is trapezoidal rule is simpler and less accurate. Simpson rule is usually more accurate as it approximates the curve using parabolic arcs, and the significant difference suggests that the function PV is nonlinear and higher order fitting. So Simpson rules give a better approximation.
Hello, my name is Muhammad Izul Nasrul with matrix number 84541. So today I'm going to solve question 3. In question 3, we can solve it using two methods, which is Euler method and Runge-Kutta method. So these are all the value given in the question, and we need to get t from 0 to t equal to 1. So for Euler method, these are two formula that we are going to use, and we just sub in the value that we have into this formula, and then we get all this answer, and then at the end of our finding, we can get V at 1 second is equal to 3.468 volts. And then for Runge-Kutta method, these are all the general formula that we're going to use to solve using Runge-Kutta. So So in this table, these are all the calculated value that we get from using this formula, and then these are step-by-step work to get K1, K2, and so on. And at the end of our finding, we're going to get V at 1 second is equal to 3.6788. For an analytical solution, we can observe that, we can get that V at 1 second is equal to 3.6788 volt. So when we calculate the percentage error, the method 1, which is Euler method, it's giving us 5.22% of error. Meanwhile, for percentage error using the second method is 0%, which means it's more accurate. So in my conclusion, Euler method is fast and simple, but it's less accurate. Meanwhile, Runge-Kutta method, it takes a long time and it's quite complex to do, but it's highly accurate.